Everyone, it's Muhammed Mert Çulha, and this is my project for EEE474. My project is about simulation of unprocessed MRI data from case-space coordinates. I simulated data obtained from MRI analysis from the case-space points. In order to achieve this, I used a phantom function, which is called sheep-logan head phantom, and it is using case-space coordinates. As far as we know, case-space image can be constructed by using phase encoding and frequency. Therefore, I used key x and key y coordinates that are in the frequency domain of an image. Moreover, this method can be applicable for nonlinear trajectories. For example, spiral projection reconstruction MRI can be tested, or just projection reconstruction MRI can be tested. In this report, I will demonstrate the implementation of my design of the project and give information about the steps that I made. I will show the GUI design and the simulation part of my project. In the code definition part, as a first step, I created a function in MATLAB which is called phantom. It requires two inputs that are key x and key y values in the frequency domain of an image with respect to x and y axis. In image processing toolbox, there is a function called phantom.m that generates an image of a head phantom. It has two inputs, P and E. P is the grayscale image, which includes an ellipse that has some small ellipses inside, and E is a matrix that represents an ellipse in the image with its rows. E matrix has 6 columns, and each column defines a different parameter. In the first column, it corresponds to additive intensity value of the ellipse. Second column corresponds to length of the horizontal semi-axis of the ellipse. Third column corresponds to length of the vertical semi-axis of the ellipse. Fourth column corresponds to x-coordinate of the center of the ellipse. Fifth column corresponds to y-coordinate of the center of the ellipse. And last column is the angle between the horizontal semi-axis of the ellipse and the x-axis of the image. After this process, I check the phantom function whether it exists in MATLAB. According to checking operation, I assign P to an empty array and E to modified sheep-logan that I found from the website of MATLAB. On the modified sheep-logan head phantom, I do some changes about this function. I increase the contrast by changing the modified one. Then I use this function. After this process, I assigned each of the column as a parameter in MATLAB. However, I scaled it according to the field of view because there is a default value that I made at the beginning of the function. I created the column vectors of case-space coordinates that are key x and key y values as I mentioned before. The step was followed by real space calculation of x and y values. And also I calculated the angle of the projections as the difference of an angle of key and theta values in the code, where key represents complex number as key x plus j key y. Moreover, I calculated each of the ellipses and case-space values individually. After the calculation, I sum all of the signals and reshape them all. Finally, I did the demonstration of the image with the corresponding GUI design by using the proper inputs. And there is a condition that if we cannot gather any output, I set the summation of the signals as 0. The following graphs introduce the GUI design of my MATLAB function as a sample. Figure 3 is the illustration of head phantom. Figure 4 raw data after simulation of case-space values, and figure 5 is the reconstructed 2D FFT image. In the result of my simulation, the implementation of the phantom function helps us to simulate MRI data by using the case-space coordinates as we know. In this part, I used MRI data provided by MATLAB and load it into my main function. I used MRI data for my function as an input. In this part, I implemented projection reconstruction and spiral projection reconstruction MRI techniques. Furthermore, using the data inside the loaded MRI, I can gather the raw MRI data in an analytical way. We know that image is reconstructed as 2D FFT, as I mentioned in introduction, which means that FFT operation is necessary for this design. In general, this function helps me to test nonlinear case-based trajectory MRI data. When I loaded different parts of the MRI, I saw different paths of case-based trajectories as illustrated in the figures below. In the first example, I will look at the first column of the matrix and second column of the matrix as an input. When I tested those two inputs, I gather two results, the head phantom and the raw data of those data. In the second example, I used 121th column and 24th column as an input for my function. As a result, I have a different paths, just different from the example 1, which means that there's a different raw data of this simulation. In the conclusion part, I see that I can get a raw data from each nonlinear case-based trajectories of MRI data in a graphical way. In the process of the simulation, I used sheep logan function provided by the MATLAB, and I made some changes to increase the contrast. That's why it's a little bit different from the original one. Moreover, we know that the case-based coordinates are 2D matrices. It's of course related to frequency and phase codes. In the reconstruction of the image process, we use 2D FFT function. As we can see, the results are quite predictable. Those are my references. Those are my appendix parts. As we can see, I made a default value. And this part is the simulation of my test data. Thank you for listening to me.